Hello, my name is Ben and welcome to this math video tutorial on proof by induction. So we had talked about some other proof techniques that we did in the last video. We talked about proof, direct proofs, proving things directly. If we do the if P then Q, we assume that P is true and then prove that Q is true. And now we also looked at proof by contradiction, where we assume that P was true and then we assume that Q is false, and then we use those two facts or assumptions to obtain a contradiction, and then to show that the statement, the original statement, is true. Proof by induction is where a technique, kind of one of the last techniques you want to pull out of your tool bag of proofs, and basically involves usually, if you're thinking of everything as the whole, like with the natural numbers, if you wanted to prove everything, for all, let's say n in the natural numbers, so the way it is structured is you're going to start out, saying let, P of n be a statement, and P of n is this is kind of a statement that involves with the natural numbers. So we're basically using the natural numbers as our set. So we're considering all the numbers like 1, 2, 3, and so forth. And then what we do is we have this base case that we do. We check to see that the first value, n equals 1, P of 1 is true to start it off. And then once we do that, once we see that P of 1 is true and that checks out, then we're going to say, let P of K be a statement. And we're just kind of restating like P of n, but we're using the variable K this time. And that's also with the natural numbers as well. So we're just using K in place of n, and then we're going to prove that if P of K plus 1 is true. So you can kind of think of this as like, kind of like a domino theory. Say you got a bunch of dominoes here. And you have a bunch of dominoes here. This is like the first one, the second one, the third dominoes, and then later on you have the K domino and the K plus 1 domino. So first of all, we check to see if the first domino is going to fall down. We see that that's going to be true, so that'll be okay. And then later on we'll go to this K domino. Later in our stack of dominoes, they're going to be falling down, and if we see that that's going to fall down, then the one after it, the K plus 1 domino, that's going to fall down as well. We predict that one's going to fall down as well. So that's kind of how basically proof by induction works conceptually. So the best way to illustrate proof by induction is just by looking at some examples here, and then go from there. So let's look at some examples. So we'll do a new board. And here's an example. So we want to prove, let's say that we have the sum of from 1 to, let's say, n, big N, or better yet, let's rewrite this. We'll do I equals 1 to n of I, and then that's going to be equal to n times n plus 1 over 2. So we need to prove that that's true. And so yeah, you can use any letter you want, but I guess in this case we could use I. But since we're dealing with n, we should probably stick with just lowercase n. So let's do that instead, using our index as n. So you can use any letter you want, but since we discussed it earlier, we should stick with that. Okay. So the way that we're going to prove this is we'll just say, let P of n be statement and basically this is going to be our statement, P of n, sum of n equals 1 to big N. Our upper limit of little n is equal to the big N times big N plus 1 over 2. So there's P of n. And then we gotta check that P of 1 is true. So check P of 1. So the way we do that is we're just going to plug in 1 for n. So n equals 1. And see that it's true on both sides. And we just plug in 1 times 1 plus 2 over 2. And we see that we get 1 times 2 over 2. And 2 over 2 is 1, so obviously that's true. So 1 equals 1, that's good. And then now we're going to let P of k be a statement. And it's basically going to be kind of the same thing, except we're just replacing it with k. So k equals 1, and we'll just do big K here. So we have adding up little k, and it's going to be k times k plus 1 over 2. And then let's prove P of k plus 1. And so the way that we're going to do that is we're going to add a k plus 1 to both sides of the equation, because what we want, the goal that we want, is we want to get k plus 1 here, and with the k plus 1 here plus 1, that's going to be k plus 1 is k plus 2, and then we're just going to get that all over 2. So that's what we want on the side. So when we add this up, we get 1 plus 2 plus 3 plus all the way to k, and then we're going to add k plus 1 on the left side, and then that's going to equal, on the right side, we're going to have k times k plus 1 over 2 plus k plus 1, just adding k plus 1 to both sides. And then we just got to do some algebra. So that's going to be equal to k times k plus 1 over 2 plus 2 k plus 1 over 2. And then all we need to do is add the fractions together because we have a common denominator now, and we see that when we add k plus 1 here, these are like terms, we're going to get k plus 2. So this will be k plus 2 times k plus 1 over 2. And then we can just reorder this. So that's going to be k plus 1, because that's what our k is replaced with, is k plus 1. So everything is 1 more than what k is. And then times k plus 2, that's the same thing as k plus 1. And then plus 1, kind of that in parentheses, all over 2. So we see that everything that had k, we just have 1 more than that with k. So k is k plus 1, k plus 1 is k plus 1 plus 1, which was k plus 2 here, and then all over 2. And then there's our result, so we proved it. So then we can say therefore, and this is symbol for therefore, there's 3 dots, like in a triangle. We can say P of n, our original statement, is true. And then we can put a diamond there to indicate we're done with the proof. Okay, so it seems like there was a lot of stuff that was going on here in proof by induction, but we can recap, kind of summarize what we just did here in this problem. So the first step that we did is we let P of n be a statement. And that statement was actually the statement we're trying to prove here with the natural numbers. And that was that summation of n equals 1 to big N of little n. And that's going to be big N times big N plus 1 over 2. There's our P of n. And then the next step, we're going to check P of 1, because that's our first natural number, n equals 1. And so we just replace the little n with 1. And we know that n equals 1, our upper limit's going to be 1, because we're just adding one number and we should get 1. And we did it on the other side and we saw both sides are equal, so we got 1. Just substituting n equals 1. And then our third step was to let P of k be a statement. So basically we're just restating what P of n is in step 1, and we're just replacing everything with the letter k, the variable k instead of n. And then this is of course the big K, and the big K's go over here with the k and k plus 1. And this is little k equals 1 down there. And then the last step is like the induction step, where you have to prove the P of k plus 1. And that's the proof part, where we added k plus 1 to both sides of the equation. And we worked on the right hand side of the equation here, leaving the left side alone. And we see that when we did that, doing some algebra, getting a common denominator of 2 here, we see that if we add the like terms with k plus 1, we get the k plus 2. Adding k and 2 together, you get k plus 2, and then k plus 1 is our like term over 2. And then we just rearranged, we just put the k plus 1 here, and then the k plus 2 goes over there. And we just replace k plus 2. We know k is replaced with k plus 1 and then plus 1. So it's just important to notice that k plus 2 is the same as k plus 1 plus 1 over 2. And then we say therefore P of n is true, and then that concludes the proof. Okay, so let's look at another example. Need a new board here. And this time we're going to do another summation. So we're going to prove, let's say 1 plus 2 plus 3. Well, wait a second. No, we just did that. 1 plus 3, we're just adding the odd numbers, 5 plus all the way to 2n minus 1. And we're going to say that's equal to n squared. So we want to prove that that is true. Okay. So, adding up all the odd numbers, the summation, the n partial sum is going to give us n squared. So we did not write this in summation notation, but that's okay. So we can just say proof, let p of n be this statement. And instead of writing all this out, I'm just going to underline everything that would go right in this spot here. So let p of n be this statement. So that's what you would write down in place of that, just to save some space there. And then let's check that p of 1 is true. Check p of 1. And when we do that, we see that we get on this side, on the left side, we get 2 times 1 minus 1. That is equal to 2 minus 1 is 1. And then if we check on the right side, we plug in 1 in place of the n for n squared, so 1 squared equals 1. So we see that that is true. 1 equals 1. So it's true. And then now we let p of k be statement. And then this time you're just going to replace all the n's with k's. Okay, so 1 plus 3 plus 5 plus all the way 2k minus 1 equals k squared. And then now let's prove p of k plus 1. That's the induction step. So here's p of k plus 1. The big time part of the proof coming up. So what we're going to have to do is our summation, what we're adding is 2k minus 1. So what we're going to have to do is add 2. So what we're going to have to do is, let's write this to the side. So this is kind of what we're doing here. We're going to be adding this to both sides, 2k plus 1. We're replacing k with k plus 1, and then minus 1. So this is what we're going to be adding to both sides. To keep that equation balanced. So there we go. So when we do that, we get 1 plus 3 plus 5 all the way to 2k minus 1 plus the 2k plus 1 parentheses minus 1, and then we're going to set that equal to k squared plus 2 times k plus 1 minus 1. So that is what we just added to the right side. Now at the end of the day, what we want is on the right side, we want k squared to be k plus 1 quantity squared. We want that summation to be like that, because that's what k plus 1 is going to look like, k plus 1 squared. So we have to work all of this out right here on the right side and show that that's going to be equal to this part right here, k plus 1 squared. So let's work that out. So just doing some algebra, we have k squared plus, we're going to distribute the 2 to the k and the 1, so that's 2k. 2 times 1 is 2 minus 1, and that's equal to k squared plus 2k plus 2 minus 1 is 1. And we see that if we factor this is a perfect square trinomial, k squared plus 2k plus 1. That is the same as k plus 1 times k plus 1, because factors of 1 are 1 and 1 that add up to 2, and we can rewrite that as k plus 1 to the second power, or squared, since we have 2 of those. And that's where our goal was. We achieved that. We got k plus 1 squared. And then that is the proof. So then we can say, therefore, our original statement, P of n is true. And then you could say for all n, for all natural numbers. For all n. We didn't do that in the last proof. We didn't say for all n and n, but probably a good idea to do that, just to make sure, clear to whoever's reading your proof that they know this, that you're involving the natural numbers. Okay, so of course at the end of the proof we want to put a little symbol, we'll stamp a QED on that to say we're done. And that's it. That's it for the proof. Okay. So that one required a little bit more work to do. But it was the same principle. Just recapping, we did exactly what we did in the last proof, stated P of n's statement. And we used this statement above, this summation right here is P of n. And then our next step, we checked P of 1 to be true. So we just put 1 on both sides of the equation. And we saw we got 1 on the left side, 1 on the right side. So 1 equals 1 is true. So that checked out. And then step 3 was just to restate, P of n as P of k. We're just replacing the variable n with the variable k to use that. And then our next step is to prove P of k plus 1. And then that's where we put the k plus 1 in for all the k's that we see. We only see 1 k here, and the 2k minus 1, that's the term we're adding up. And so we replace that k with the k plus 1 and insert in our parentheses, because we know that 2 is being multiplied by that, and then minus 1. And then we just did that to the other side with the k squared. And then all we do is we work on the right side of the equation step by step until we get k squared to turn into k plus 1 squared. That's what we wanted, and that's what we got after factoring. And saw it's perfect square triangle. And then, last step is just to conclude, right? Just saying that P of n is true for all n and n, all the natural numbers. Okay, so now what we're going to do is we'll do one more example, and we're actually going to do an inequality this time, not an equation. And so it's a little different, but it is the same idea. So trying to get a new board here. There we go. Took a few seconds to show up there. And now we're going to say what we're going to do is, before we have a statement that we're going to prove, we're just going to compare, these two expressions and then make a claim about it and see if we can prove it. So let's say we compare, n factorial and 2 to the n. These two different functions here. And then we're going to say, find a condition, find which one is greater, and for what values of n. And maybe put parentheses for s, because it may just be one value, but just looking at probably more than one value. So what values of n, and then prove. Then we'll say prove your claim. Okay, so we'll do some scratch work here on the side. We know we can make a little table here, and we have n. We'll have n factorial in this column, and then we'll have 2 to the n in this column. And then we'll just start out with a few values for n equals 1, 2, 3, 4, let's say maybe 5, and we'll stop right there. This will kind of give us an idea which one's going to be the greatest. So if we let n equal 1, well, 1 factorial is just 1, and then 2 to the first power is just 2, so 2 the n's greater. 2 factorial, that's going to be 2, and 2 to the second power, 2 squared is 4, so 2 to the n's still greater. 3 factorial is 6, and then 2 to the third power, 2 cubed is 8, so we can still see 2 to the n is beating n factorial. But let's say if we get to n equals 4, and 4 factorial, that's 24, and 2 to the fourth power is 16, so n factorial is in the lead, and then 5 factorial, that's 120, and 2 to the fifth power is 32. So we can start to see a pattern here that n equals 4, we start to see that n factorial is overtaking 2 to the n. It's actually greater than. And so let's see, how about n equals 5, n factorial is bigger, 120, a lot bigger than 32. And if we did 6, n equals 6, we get 720. And we see 2 to the 6, that's 64. So we can make a claim. We can say, for all n, let's say greater than equal to 4, n factorial is greater than, strictly greater than 2 to the n. So that looks like a true statement, right? But to know for certain that it's a true statement, we need to write a proof to make sure, show why it's true. And that's when we're going to use proof by induction. We're going to use proof by induction to prove this claim. So this is our claim right here. So let's prove it. Let's prove the statement. So we're going to start just like we've done. We're just going to say let, P of n be our statement. For all, and we can abbreviate this, right? Because for all means upside down a for all n greater than or equal to 4. We know that n factorial is greater than 2 to the n. And what is our first value? This time it's not going to be 1, right? Because we used to doing 1. Our first value is where the inequality is, right? And it's at n equals 4. So we need to check P of 4. Because that's where the inequality begins. Check P of 4. So we'll do that. So we'll plug 4 factorial. We see that that's equal to 24. And then we see that 2 to the 4th is 16. So we know that 4 factorial is greater than 2 to the 4th. So that's true. So that's okay. That's our base case. P of 4 we know is true. Okay, so now we're going to let P of k be statement. Just restating, kind of like P of n, but replacing it with k. So for all k greater than or equal to 4, k factorial is greater than 2 to the k. So just replacing all the n's with k's. And then we do the induction step. Prove P of k plus 1. Okay, so let's see here. So what we're going to have to do is, to do P of k plus 1, we're going to have to start on the left side here. And we're going to replace k with a k plus 1 factorial. Okay, and then we know that k plus 1 factorial, that is equal to k plus 1 times k factorial, right? You would agree? And now what we can do is we need to replace this k plus 1 with some value. What is that equal to? Well, we know that we can do some scratch work here on the side. We know that k is greater than or equal to 4 for our inequality here. So if we did k plus 1, just adding 1 to both sides, we see that k plus 1 has to be greater than or equal to 5. So we can say that this k plus 1 times k factorial, we can say instead of equals to, what we can do is, let's use black here. So we'll replace that with a greater than or equal to sign. It's greater than or equal to, and then we'll replace that with 5 times k factorial. But if we look at our scratch work, we do k factorial times is greater than 2 to the k. We can see if we multiply 5 to both sides, we see that this is going to be that 5 to the k factorial is going to be greater than 2 to the k times 5. But what we want is we want k plus 1 factorial to be greater than 2 to the k plus 1, right? Well, what's 2 to the k plus 1? 2 to the k plus 1 is 2 to the k times 2, right? So if we have 2 to the k times 5, that should be greater than 2 to the k plus 2, right? So there we go. So we can say that's actually greater than 2 to the k times 2, because 5 is greater than 2. And then we can see that 2 to the k times 2 is actually equal to 2 to the k plus 1. And there we go. So we saw that, so we see that k plus 1 factorial is actually greater than 2 to the k plus 1. And then after that, you can just say, therefore, your original statement, P of n, is true. Just try to fit that in there. And we'll put a smiley face next to that one. That one took a little work to do, but we're done. So this one was an inequality. It was a little tricky to prove. Sometimes the inequalities are. The equations can seem to be a lot more straightforward. And you can kind of see why, because you have to do a little scratch work on the side to see what direction you're going when you're trying to prove it. But just to recap, what we did in summary is at first we compared n factorial and 2 to the n. And we did the first few natural numbers, and we see that 2 to the n was a little bit bigger than n factorial. But then once we got to n equals 4, we see that the n factorial actually gets larger, a lot larger, as you can see when as n gets larger. So we know that without a shadow of a doubt that for n greater than or equal to 4, we see that n factorial is greater than 2 to the n. And that was our claim, and that's what we wanted to prove. So we had our P of n's, our statement right here. We stated that. We checked P of 4 because that's the first value in the inequality. That's the first value we see where n factorial is greater than 2 to the n. And we see that that was true, just plugging in 4 on both sides of the inequality. So 4 factorial is greater than 2 to the 4th. And then we restate again using k instead of n, so that's P of k is our statement. So just replacing all the n's with k's. And then we prove that P of k plus 1, our reduction step. And then we start on the left side of the inequality. We do k plus 1 factorial. And then we see that that's k plus 1 times k factorial. And then we do a little scratch work on the side. We know that k is greater than or equal to 4. So k plus 1 has to be greater than or equal to 5. And then that's where we replace that with a 5 there. 5k factorial. And then we see that if we multiply that to both sides with the 5 there, k factorial is greater than 2 to the k. We have 5 factorial, 5 times k factorial must be greater than 2 to the k times 5. And we also see that that is actually greater than 2 to the k times 2, because 5 is greater than 2. And 2 to the k times 2 is same as 2 to the k plus 1, because 2 is 2 to the first, and you just add the exponents, k plus 1 right there. And so you can see that k plus 1 factorial is greater than 2 to the k plus 1. That was our P of k plus 1. Just replacing all the k's in our inequality with k plus 1. And therefore we see the original statement, P of n is true. And then maybe you want to put at the end, for all n greater than or equal to 4, just to restate that. Okay, so again, my name is Ben. I want to thank you for watching this video on proof by induction. There was a lot of information here to digest and understand, but hopefully this will give you some kind of footing, somewhere to begin. These problems, they are kind of challenging, so if you feel like you need to pause or rewind the video, that's always a great thing about watching these video tutorials. And instead, I'll look forward to doing some more math video tutorials with you, and I hope you have a great day. You take care. Bye bye.